Right. So the material here, chemical reactions and introduction, that's what we're going to cover today. This chapter plus this chapter, which we'll cover in our next session, reactions in aqueous solution, will be part of exam 4. All right, so up to this point, we've learned we've learned the symbols for all the elements, which would be the alphabet, the letters of chemistry. And then we've learned how to write words in chemistry, which is chemical formulas for compounds. We've learned how to name them. We've learned how to write the compounds from the names. Now we're going to put those compounds together, compounds and elements actually, together in chemical reactions and learn how to write the chemical reactions so that we can create sentences. First, we're going to look at how do we know a chemical reaction has taken place? There are clues. Remember at the very beginning, I suggested that you try to develop an intuition for chemical reactions, creating a link between the macroscopic world and the microscopic world, the world that you can see, that you can touch, you can smell, and what's actually happening underneath at the atomic level. Well, these are some of those macroscopic clues that tell you a reaction may have taken place. They often give visual signals like changes of color. Now, for sure, a change in color doesn't necessarily denote a chemical reaction. You can get changes in color without a chemical reaction, but it's an indicator, a clue. Many reactions, though, don't absorb light or emit light in the visible spectrum, so we can't see them, not with our eyes. So we need other clues. In addition to color change, one thing that might happen is if you put two solutions together, they may react in a way that forms a solid. And I don't necessarily mean a solid that's like a brick. They could be very finely divided, and usually are, finely divided solids that eventually settle out. These are called precipitates. That's definitely a chemical reaction. Some chemical reactions evolve gases, and if the matrix is liquid, especially, the formation of the gas is easy to detect as bubbles. You can get bubbles formed in solids too, but those reactions are a bit exotic for our purposes in this course. Very often, a reaction will either evolve heat or absorb heat from the surroundings. And this may involve, but not necessarily produce, a flame, such as the combustion of methane or natural gas in an oxygen-rich environment. You will get a flame. Those are major contributors, clues that a chemical reaction has occurred. Here we have an example of the evolution of a gas in a chemical reaction. Right? So what's happening here is this 9-volt battery is submerged in water that has maybe a little bit of acid in it to make the water conductive. If I haven't said before, pure water, distilled water, is an insulator. It does not conduct electricity at low voltages because there are no mobile ions sufficient in quantity to conduct the current from one terminal to the other. But if we make the water conductive by adding just a little bit of acid, then we can get the power transferred from one pole to the other, and in the process provide enough energy to break water into its components, hydrogen and oxygen. Here's another clue. What we see here is by adding hydrochloric acid to a red solution of cobalt nitrate, we turn the solution blue. The color change is an indicator of a chemical reaction here. Here's an example of a reaction where we combine two solutions, one sodium dichromate and the other lead nitrate. Now, in the separate solutions might have a color, but they're transparent. They are bona fide solutions, homogeneous mixtures in aqueous solution. So the water is the major component, and sodium dichromate in one, lead nitrate in the other are the minor components. But when we put those two solutions together, now the sodium dichromate and the lead nitrate have an opportunity to combine, and we get a reaction that produces a yellow precipitate, a solid. All right, so how do we write chemical reactions? Well, the sentence structure for a chemical reaction is reactants are always on the left-hand side, products are always on the right-hand side, and we put a progress arrow in between to show that we're progressing from reactants to products. This is known as a chemical equation. In this case, we have methane, and we write the correct compound for methane, which is CH4, and it's reacting with oxygen. Remember, oxygen is a diatomic element, so you have to write it O2 with a subscript of 2. That produces carbon dioxide, which is a type 3 compound. That's why we say carbon dioxide, 2 nonmetals, and water. Those are the products. One thing you'll notice, I think it's on the next slide. I'll call attention here, though. One thing you'll notice is that we don't have the same number of atoms of each element on both sides of the equation. Now, carbon, yes, we have 1 carbon on the reactant side, 1 carbon on the product side, but we have 4 hydrogens on the reactant side and only 2 hydrogens on the product side. So we know immediately that this equation is not balanced, and it is, in its current form, it is violating the law of Lavoisier's law of conservation of mass, because if we don't have the same number of elements on both sides, atoms of elements on both sides, then we don't have the same mass on both sides. So we have to account for the reactants and the product atoms during our balancing procedure, which we'll come to in a few minutes. All right. Polyatomic ions, we learned those during naming compounds. Polyatomics sometimes retain their structural integrity as reactants and products. So you'll find the polyatomic on the reactant side and the same polyatomic on the product side, and none of the atoms inside the polyatomic have been stripped away. So that allows us, when we balance equations, to treat polyatomic ions as a balancing unit. And we'll come to that again shortly. So if we count up the number of atoms in our reaction, methane plus oxygen yields carbon dioxide plus water, we find that the unbalanced equation is demonstrated here. The balanced equation requires that we need more oxygen on the reactant side and more water on the product side. And we designate the number of atoms and molecules on either side. We modify it by a coefficient. So if we write the equation, methane plus oxygen yields carbon dioxide plus water, we cannot change the formulas as written. Those are fixed, they're chiseled in stone. The only way you can change the numbers of those atoms is to incorporate a coefficient, a prefix, if you will, in front of each one of these. If you do that, now what does that mean? That means we have 2 water molecules and 2 oxygen molecules, 1 carbon dioxide and 1 methane. And by doing that, we balance the number of atoms of each one. And you can see the tally down here, 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, 4 oxygens. Now, technically, this equation is balanced. We often, when we write the compounds, we include the states. Sometimes the states are essential to understanding the progress of a reaction and the mechanics of balancing a reaction. Sometimes they're not, but it's always a good habit to include the state in case you need it later. Well, in our example here, methane is a gas, oxygen is a gas, carbon dioxide is a gas. And depending on whether the reaction is reported at standard conditions or whether it's reported at current conditions, water could be either a gas or a liquid. This reaction produces a lot of heat. So the water that's produced could possibly be a gas, a water vapor. So we don't know, based on what we were given, we don't know which one is correct. But we use S, L, and G for solid, liquid, gas. And then if we have an aqueous solution, we also have access to that physical state. So here we have an example of potassium metal, which before we combine them, the potassium metal is probably in mineral oil because it's very reactive. Water in the atmosphere will react with that potassium, and we'll get the violent reaction that you see in the far right image. So it's currently in mineral oil to isolate it from water vapor. Then we have the water and as a reactant, and when we combine them, we get that far right image that is showing a production of hydrogen gas as bubbles, and KOH is not visible. We just have to deduce that one. And notice also there's a flame. This is a secondary reaction. When we get, let's make room here. When we have potassium hydroxide plus water, this is a solid, that's a liquid, and it produces hydrogen gas plus in aqueous solution, KOH. But notice that we have hydrogen gas produced. Well, there's enormous amount of heat generated in this reaction. And as the bubbles rise to the surface, Now they're in contact with oxygen in the atmosphere. This hydrogen now is once again in contact with oxygen in the atmosphere and combines to produce water with a lot of heat. That's what that delta sign means in chemical terms. We're saying it produces an enormous amount of heat. Well, it produces a lot of heat here also. And this heat is sufficient to ignite. It provides enough energy to ignite the hydrogen in the oxygen atmosphere, and that's where you get that flame. So we're actually witnessing two chemical reactions. The production of hydrogen gas as bubbles shows us the reaction as written here on the slide. And this reaction is the chemical reaction of hydrogen and oxygen in the atmosphere. Oh, but this one's not balanced, so we need to balance it. I need two oxygens. That gives me 4 hydrogens. I need 2 there. Now that equation is balanced also. Oops. That was an error. Potassium metal plus water produces hydrogen and potassium hydroxide. Now here's just an example to illustrate what we've learned so far. When we shine a blue light on a mixture of hydrogen and chlorine gas, the elements react explosively to form gaseous hydrochloric acid. Well, we identify the reactants from the text, and the product is also given as gaseous hydrochloric acid. Okay, there's a problem with that statement. Hydrochloric acid is only named an acid when it's in aqueous solution. So gaseous hydrochloric acid is excessive. It's not hydrochloric acid if it's a gas. It's hydrogen chloride gas. Okay, now back to the problem. The unbalanced equation then is this one right here, as written. We know it's not balanced because we have 2 hydrogens, 1 hydrogen here, 2 chlorines, 1 chlorine there. We know it's not balanced. But that answers the question up to this point. How would we balance it? Well, very simply, we just put a 2 right here. 2 hydrogens, 2 chlorines. And that equation is balanced. We have to conserve atoms. We cannot create matter. We cannot destroy matter. We cannot transform one element into another by way of a chemical reaction. Now, we can transform elements from one to another, transmute them, we say, in nuclear reactors or in atomic weapons, but that's not chemistry, at least not for this course. So we have to preserve the number of atoms, we have to preserve the elements as those atoms on both sides of the equation. All right. Now, for the vast majority of chemical reactions, we know the reactants because we, as the experimenters, are putting them together. But what are the products? Most of the time, we have to determine the products by observation. We have to run tests. We have to determine what the products happen to be. There are a small number of reactions that we can predict. Excuse me. and some others with experience that some chemists can predict because they've uh, they've modified the reaction conditions to produce the desired outcome. But for the most part, products have to be experimentally determined, and that means that for you as a student, we will have to give you those products in order for you to write the complete reaction. Just to hammer home this particular point, the identities of the compounds cannot be changed while balancing a chemical equation. All right. So we've done this already. We've read the description of the chemical reaction and determined the reactants and products along with their states. That's our example. And we write the correct formulas for the elements and compounds. That's the first step. So we know what the diatomic elements are, and we know how to write compounds from their names. Then you write the unbalanced equation. We've done that before. Here's our example. Well, that's a different example. Then your textbook and many chemistry textbooks tell you to balance the equation by inspection, starting with the most complicated molecule and keeping an inventory. All right. Balancing by inspection is a catch-all term, and it doesn't tell you how to do it. It doesn't give you any instruction on shortening the process, providing evidence for balancing an equation while you're doing it so that you can make logical steps, right? So this statement, balance by inspection, is actually the author's unwillingness to describe that process for the reader, for the student. Now, there are some chemical textbooks that do include instructions, but there's still some that say by inspection, right? So I'm going to give you a procedure for balancing equations with some helpful hints along the way, and we're going to get there in just a minute. All right. So the first thing you do is set up your budget. This is what I call my budget method. So if we write the correct here, plus oxygen yields water. And notice I left gaps in here for coefficients. The first thing I do is set up a budget. What elements are in the reaction? So I put hydrogen over here and oxygen over here. Those are the only two elements. Then I do an initial tally. I keep doing inventory. We have two hydrogens and two oxygens on this side. On that side, we have two hydrogens and one oxygen. Okay, so reactant side, product side. This allows you to instantly determine whether your equation is balanced or unbalanced. And we know that it's unbalanced right here. Okay, so we've done that. We've counted up the number of atoms on both sides of the arrow. Now we need to incorporate coefficients to modify our inventory toward equal numbers of atoms on both sides of the equation. Okay, so hydrogen is already done, right? It may change, but for now, we only have oxygen as our element, our first element to balance. So in order to make this one 2, I need a 2 coefficient. That gives me 2 oxygens here. I readjust. Oh, but now I've changed the number of hydrogens to 4, right? That happens. Whenever you put a coefficient in front of a compound, you're changing more than one element. So now that I've got 4 here, I come back over here and say, okay, what do I do to make 4 hydrogens? I put a 2 here. That's 4 hydrogens. And now we can see at a glance, we're balanced. One other step that may be necessary, not always, but sometimes, is if you have coefficients, and remember, this is 2, that's 1 and 2. If you have coefficients that can be evenly divided by some divisor, like a 2, a 3, or a 4, then you reduce all the values by that factor. So if we had a 4 here and a 2 here and a 4 there, that's not the simplest whole number ratio. So we divide everything through by 2, make that a 2, a 1, and a 2. That would be the preferred coefficient array for our equation. There are some occasions where fractional coefficients are allowed, simply because the definition for the reaction demands that we use fractional coefficients. Sometimes we use fractional coefficients as an intermediate step in our balancing procedure, but we get rid of them before the end of the equation, before we publish the results. So notice that the ratio 2, 1, 2 is the same as 4, 2, 4. Once the equation is balanced, that ratio is fixed and cannot be changed except unless we do the same multiplication or division to everything in the equation. All right, so there's our balanced equation. And it could be that, but we prefer the former. Okay, now here's some hints, some helpful hints. And we're going to do some examples that use these hints. First one is if there's an element in the equation that only appears as the element on either side, reactants or products, save it till last. Why? Because any coefficient that you put in front of that element only changes that element. If you save a compound to last, then you put a coefficient in front of the compound. Now you've probably unbalanced one of the other elements. So we save the elements to last. Freestanding elements we save to last. For instance, here we have this oxygen by itself. Save it to last. I got an error there. That should be a subscript. And that includes any elements, monatomic, diatomic, tetratomic, octatomic. As long as it's just one element, then save it till last. We tend to hold water till toward the end. Sometimes we can do that and sometimes we can't. Here's a hint for fractional coefficient. if we're going to balance this equation, sometimes it's necessary to use a fraction, like 25 halves of oxygen, to give us 25 oxygens. So on this side, we have 2 times 8 is 16, plus 9 is 25. And if we want to balance the oxygen last, we need 25 halves. Then we can get rid of the half. Now that the equation is balanced technically, we can multiply the entire equation through by the same value, number 2. And that will change this one to 2. This one gets rid of the fraction. This one makes it 16, this one 18. Now we have all whole numbers, and they cannot be reduced further by division. That's known as the fraction trick. Here's another one. In the case where you have an element in only one location on the reactant side and the product side, and in this case, we're saying hydrogen is part of ammonia on the reactant side and is part of water on the product side. But the numbers of hydrogens on the reactant side are an odd number and an even number on the product side. So how do you balance that situation? Because if you multiply by one value on one side, you still haven't balanced it for the other side. So in that case, we use what's called cross multiplication. We take the coefficient 2 from water, put it in front of ammonia, and take the not the subscript for 2, make it a coefficient, and the subscript 3, and make it a coefficient on the other side. And now you have 6 hydrogens and 6 hydrogens. That's a quick and easy way if the element occurs only in one of 2 places, on the reactant side or the product side. If it's in multiple places, then you are not likely to benefit from this trick. All right, now here's the polyatomic hint that I mentioned earlier. In this case, we have ammonia on this side, ammonia on that side, phosphate on this side, phosphate on that side, and they were retained in their entirety, both sides of the equation. They can be used as balancing units. So when I set up my budget, I've got ammonia, phosphate, calcium, and chloride as balancing units or groups. And then we complete the process from there. But before we do that, I want to go to a simpler equation and run through an example first. We'll come back to this slide. Let's do this example. Okay, we have, what is this? Name that compound. Is it a type 1, type 2, or type 3? It's not a type 3 because we have a metal nonmetal. So is it a 1 or a 2? Well, iron is one of those elements, the transition elements, that can have multiple possible charges. So it's a type 2. It's a type 2 compound. That means we have to determine the charge on the iron before we can name it. Well, oxygens are always considered 2 minus. So that means iron is 2 plus. So we would write iron 2 oxide. Okay? All right. So this reaction produces, reaction with oxygen produces Fe2O3. All right. Now, what's the name of that compound? Well, again, it's a type 2. We have to determine what is the charge on the iron. Well, with 2 minus here, we have 6 minus total. That means 6 plus total is required for this one. And each one of those irons must be a 3 plus. times 2 is 6 plus. So this one would be iron 3 oxide. Okay? All right. So let's get back to balancing the equations. Set up our budget. We have iron and oxygen only. On this side, we have 1 iron. We have 3 oxygens. On this side, we have 2 iron and 3 oxygens. Okay? So we see right away that it's not balanced and that we would have to go to the iron to get a balanced equation. Also, we want to be sure and hold that oxygen till the last, which is a non-issue now because it's already balanced at this point. But if we balance the iron by putting a 2 here, right, that changes the oxygens. That's 2, 4 oxygens there. Okay, now how do we get around this one? Well, notice that oxygen occurs in 2 places. We've already got 2 oxygens here. That means if we balance, in order to balance the oxygens, well, let's say we want, all right, we've got 4 oxygens here. We need 4 over here. What we're going to have to do all right, sum of the coefficients is 7. All right. This may take a while, but if we're going to get 4 oxygens on this side, we only need to add 1 more oxygen, which is a problem. If we put a 2 here, that makes 6 oxygens. And that means we need 4 irons. So we've made this one 4, this one 6. This one now is 4, and 4 plus 2 is 6. So we got lucky. Balancing the ones like this, we don't even have to touch that oxygen. Our equation is now balanced. And we add up the coefficients to answer the question. We have 4 plus 1 plus 2 equals 7. Don't forget the coefficient in front of oxygen. If there is a compound or an element in the equation and you don't see a coefficient, the coefficient is always 1. Okay. We can do another one before we go back to, let's do one more. We'll do one more. This is an unbalanced equation. Okay, we have several examples here. All right, let's balance the equation first. Right? Oh, carbon dioxide, sorry. Calcium, what is the, let's see, this is calcium oxide. That's carbon, right? This is calcium carbide. right? IDE on the end of carbon. And then carbon dioxide. Okay, so we have calcium, we have oxygen, and carbon. We have one calcium, one oxygen, one carbon. Over here we have one calcium, two oxygens, and two carbons. Okay? Save the carbon to last. We can either take oxygen or carbon to balance. I'm going to go with, oh, my mistake. 1, 2, 3. There we go. So the temptation is to balance this carbon, but that's an element. So we're going to save it to last and do the oxygens. We have two oxygens here. Let's make two oxygens there. That changes the calcium to 2. Right? So let's count it up to be sure we're not. 2, 4, 5. 2, 4, 5. 1, 2, 3, 6. 1, 2, 3, 4, 5, 6. Okay. So we've got all these balanced. Now we need to get calcium back in line. So we need 2 calciums here. That changes the carbon to 4, and 1 is 5. Correct? Two calciums, 2 oxygens, 4, 5. Yeah. Now we can use a coefficient of 5 here, and 2, 2, 5. We're balanced. So the preferred is this one. Not all of them are balanced equations, but 3 is a possibility, only it's got a fraction. It's using fractions. And 4 is the same ratio, only it's multiplied everything by 2. So 3 and 4 are technically correct. 1 is not. It's not balanced at all. But we prefer 2. Okay. There's our preferred one. Okay, now let's go back. I won't have to draw this one on the board because I've fully animated this one. All right, there's our budget. So we have that red line shows the difference between reactants on one side and products on the other. And we do an initial tally using polyatomic ions as balancing groups. Now, I will say that when a polyatomic ion is part of a reaction and it disrupts, the reaction disrupts the polyatomic, it's not complete on the product side, then you can't use this trick. You have to do individual elements then. All right, but in this case, we have an initial tally of 3 ammonias on the reactant side. We have 1 phosphate, we have 1 calcium, and we have 2 chlorines. Then on the product side, we only have 1 ammonia, 2 phosphates, 3 calciums, and 1 chlorine. Now, how do we know these are different? Because we wrote the compounds correctly to begin with. Ammonia has a +1 charge, phosphate is a 3- charge. So we need 3 ammonias in parentheses. That's the pattern for correctly writing these compounds. And that's why I was so insistent upon your learning how to write compounds. Type 1, type 2, type 3. From the names, and to name the compounds from their formulas. Because I knew this was coming. We had to be able to write those correctly in order to generate an unbalanced chemical reaction equation. All right, now where do we start? Well, we don't have any elements in there, so we can't hold anything till last. Sometimes, if you can't make up your mind, just start at the top. And since the complexity of each of these elements is similar, right? They're all binary. The ammonium phosphate and calcium phosphate are technically a little more complex because they have more polyatomic ions. So we could pick one of those, maybe balance the calcium first, or balance the ammonium first, or do the phosphates first. I picked the calciums first. So 3 calciums here to balance the calcium on the product side. Now we reassess, and that red 1 is simply an indicator to show you the order of the process. If you saw this at the end, you would see those red numbers up there, and that tells you the order that I proceeded. And that's the way the review document, the handwritten solution to the problems that you'll find in Brightspace for the review document. I've put these numbers above the equation to show you the order that I proceeded through balancing those equations, so that it wouldn't be a confusing mess. All right, now what have we done? We have to recalculate the chlorides also. So we have 6. Now we can balance the chlorides on the product side with a 6 in front. That gives us 6 chlorines and 6 ammoniums and 6 chlorines. Okay, it shows we're approaching balance. Now what we have to do is balance the ammonias. Okay, with a 2. A 2 in front balances the ammonias with 6 ammonias on the reactant side, 6 ammoniums on the product side, but we've also changed the phosphates. So we retally the phosphates, and we get 2 there. And lo and behold, 6236, 6236. Okay, we're now balanced. And we've done these before, so we're going to skip through these slides and go to the concept check. When balancing a chemical equation, which of the following statements is false? Subscripts in the reactants must be conserved in the products. No, you write the reactants and products according to their correct formulas based upon their names and their compound identities. So A is false. B says coefficients are used to balance the atoms on both sides. That's true. Coefficients are used to balance. C, when one coefficient is doubled, the rest of the coefficients in the balanced equation must also be doubled. The key here is balanced equation. If the equation is balanced and you multiply any coefficient by a number, the rest of them must be multiplied by that same number to maintain the ratios. So C is also true. D, phases are often shown for each compound but are not critical to balance the equation. That's true. The only false one was the first one. And this is just a reminder. Okay, once we have a balanced equation, we can proceed with a process called stoichiometry. Stoichiometry actually takes a balanced equation and given amounts of reactants or products and determines the outcome for the reaction in terms of either mass volume of gas, depending on the phases. We're going to start with mass. That's the easiest one to describe. So we balanced our equation. Oh, that's as far as we're going. we'll do more stoichiometry in the next chapter. So that's all there is for chapter 6. And you have exam number 3 for chapter 8 is due tonight. Thursday, February 20th, 2025, before midnight. So that only took us an hour. And this class is, I think it's 2 hours long. Yeah. So I think that's enough for now. I will say that if you, in fact, I may share the documents. Let me stop this share and pull up other documents that you need to look for in Brightspace to help you understand this chapter and chapter 7. This helpful hints. There were slides on created from these helpful hints in the PowerPoints, but this is a separate document that you can print out. You can access in Brightspace and print out, and it should give you. Let's see, that's only one-sided. That should be good. Does it have? Yes. Okay, it's got everything in there. All right, so this is one document. Then, of course, you have, as usual, you have the review document, which is here. No, that's not it. Here. There's your review document. And it's broken up into chapter 6 and chapter 7, I think. So we should, yeah. Let's see. Skip down. There. No, that's chapter 6. Here's chapter 7. Okay. They're consecutively numbered. And this is chapter 7. Of course, you won't be dealing with that now. We haven't discussed that topic yet. So next Tuesday, we will cover this topic, chapter 7. And then, of course, you should also see at the bottom here useful information, right? There's balancing equations again. And that just means that anything you see in the review document, useful information, will also be available for the exam. If you take the exam in Brightspace, then you'll go to the module where the exam is located, and you'll find a document, a PDF document. Before you click on the exam link, be sure and have a copy of that review document printed out, because once you go into the exam, a lockdown browser won't let you back into the browser. It won't let you find that information. So make sure you have a copy of it. Polyatomic ions, okay? And you'll need this chart for chapter 7. We'll cover that later. And then here's your periodic table, okay? So you have all that available for you on your exam. Now that's the review document. Work those problems. I crossed some of them out because they're not relevant. And then you shall also find the worked problems document, which is this one. Here we go. So these worked problems will show you how I solved the problems if you can't do them yourself. And notice, like I said before, these numbers with circles around them tell you the order. So the first step I did after taking the inventory was I went and put that 4 in front of aluminum oxide. And then this one shows you that I had to rebalance these two terms, right? The aluminum and the oxygen. And then the document itself has, it looks like mostly balancing equations here. Okay. All right, so those documents you have available in Brightspace. And I think that's it. So we'll pick up with chapter 7 next Tuesday, which will be the 25th of February. Until then, get busy working those problems. Practice, practice. Repetition is going to get you where you need to be. And if you get bored working those problems, that's a good sign. All right. That's it for today.